Okay, so let me actually use the divergence theorem. So I'm going to do the same problem that we did for motivation, except I'm going to remove motivation. And on this one, I'm actually going to calculate, because it's actually easy. So I want to calculate the flux of this messy vector field x squared plus y squared, comma y squared plus c squared, comma x squared plus c squared, through the cubed, 0, 1, 0, 1 by 0, 1, oriented outwards. And you guys don't know the divergence theorem yet. Okay, so let me tell you the divergence theorem right now. So the flux, right, we could get by integrating over the surface f dotted with dA, right? Like that's what I did for motivation. I calculated each of the surfaces and then dot producted with this normal vector and blah, blah, blah. Right? And then we had to add up all these answers. But that was kind of nasty. Right? So here's the content of the divergence theorem. Instead of doing that, you can triple integrate, and that's going to be over the cube this time, the divergence of f, d volume. And again, this is kind of crap notation that I'm using, right? Because I slapped a triple integral d volume. But I'm just emphasizing that that's a triple integral. That that's going to be some kind of volume integral. You guys good with this?
Okay.
Okay, so you have to check some assumptions to apply the divergence theorem. I haven't told you what those assumptions are. Just trust me, the cube satisfies them. We'll list them in a bit here.
Okay.
Okay. They're basically the same as the kind of assumptions for greens. You need to have something that's piecewise smooth, that's closed and reasonable and orientable and oriented at least the same frickin' way.
Yeah.
You guys see that? Okay. So this thing at least is all oriented in the same direction. It's clearly piecewise smooth. It actually does enclose a volume. You guys see that? Mm-hmm. So you're going to need that at the very least. If this thing doesn't enclose a volume and doesn't have a consistent orientation, you would be posed on using the divergence theorem. That's cool. I also should check signage, and for signage, this isn't going to be, like in greens, it would be oriented counterclockwise, right? On this guy, I need oriented outwards. Cool? So what this is saying is the flux, right, is the sum of the divergences. If divergence made any sense to use as a word here, that would kind of make sense, right? Like the stuff leaving through the surface ought to be the sum of how much less dense it's getting. You guys see that?
What's the less dense?
That's what a divergence would mean.
Divergence is a scalar.
Like, assuming that I use, yeah, so divergence is a scalar, right? Yeah. Okay, so let's just do this and stop talking. So how do I do this? What do I need?
We need f.
Okay, so I need to find f, and then I need to calculate the divergence of f, right? Like, first things first.
The bounds in the cube are also really easy as far as
Oh, yeah, and the bounds on a cube are duh, right? What coordinate system are you going to pick for cube?
Spherical.
Spherical. Good answer. So go from 0 to 1 in everything, right?
Yes.
And do Cartesian.
Spherical.
Duh. Okay, so at the very least, I think that my bounds will be easy. Okay. Now, what's the divergence of f? Yeah, you need to take the idea of a gradient, right?
And dot it with.
So I need divergence of f should be the idea of a gradient dotted with f, which ought to be the partial with respect to x, the partial with respect to y, and the partial with respect to z, dotted with So x squared plus y squared, comma, y squared plus z squared, comma, comma, x squared plus z squared. Right? And I don't really expect you guys to write all this down every time, because calculating divergences is pretty easy. Right? Because what am I going to do? Take the x partial of the first thing.
2x. Yes, 2x plus 2y plus 2z, isn't that?
Yeah, so this is the partial with respect to x of the first component. Right, so the y's dropped and I got 2x. And then I did the partial with respect to y of the second component. I got 2y. And the partial with respect to z of the third component, you're going to get 2z. Okay, so we traded, right, 6 nasty frickin' surface integrals. Well, actually, they weren't even that hard. There were just 6 of them, right?
For eternal writing.
For the integral from 0 to 1 in every direction of 2x plus 2y plus 2z. Right? Which I could maybe even pull a 2 out of.
That'll save 3 pages of paper.
You can also,
Right? You guys all good with this? Okay, so let's calculate. I think we can do that.
Yes.
dx, dy, dz. Okay, so what do you get? You get 2
Integral.
times the double integral, both from 0 to 1, of, what do you get when you integrate that junk with respect to x?
1/2 plus 2y plus 2z, or no, 1/2 plus 2.
Yeah.
X squared over 2 plus yx plus zx.
Yes.
And it's 1 to 0, so you just,
And then you're integrated from 0 to 1.
So we get 1/2 y and z.
Cool. That's good?
just gonna keep.
Okay, so. No.
We don't get that anymore.
Okay, so we got 2 times the double integral from 0 to 1 of 1/2 plus x plus y.
Z, y plus
Oh, sorry, y plus c. Thank you.
dy to z.
dy dz.
So,
Good?
Okay.
So that's
2 integral 1 to 0.
2, the integral from 0 to 1 of
1/2.
1/2 plus 1/2, which just becomes 1 plus z. Or, oh, you haven't integrated yet. 1/2 y. Yeah.
Okay, fine. 1/2 plus y squared over 2 plus zy evaluated from y is 0 to y is 1 and integrated dz.
I know we missed the y, but the y ends up equaling 1, so.
Thank you. Okay, so then I get
Another 1/2.
2 times the integral from 0 to 1.
1 plus z.
1 plus z dz.
Which then becomes
Which,
z.
Can we just say it's 1.5?
yeah, we could just say it was 1.5.
So
Okay.
that's
Good. So I got 2 times 1.5.
half, which ends up equaling, 3.
Cool. 3. What does that mean?
That
there's 3 flux like the key.
Yeah, on the net, this stuff is leaving the cube at a rate of 3
It's leaking.
units per time, kind of.
The cube is leaking.
Yeah, this is a leaky cube. Right, this force is this flux is tending to go out through the cube.
It's a leaky fluid.
And the way we figured that out, right, was we didn't calculate the flux through each surface and then add them up, right? We calculated the sum of the total divergence on the inside. You guys see that? Cool, cool.
Somehow water is going into the cube spontaneously and coming out in all directions.
So be careful with that. This is signed flux, right?
I know.
And it's total signed flux. Right? So I don't know that this is going out through every surface. I just know that it tends to be more out than it does in.
if you actually calculate, it's the 3 outward ones that kind of spray out while the other 3 don't really do much.
You guys see that?
Top, right, and forward.
Yeah, so it's entirely possible that 3 of these things are kind of responsible for most of the net flux, and the other ones are just little negative bits or something.
So that'd be like heat.
Also, keep in mind, right, that this is not necessarily something that can't be compressed, that you're talking about flowing. You guys see that?
Hmm.
Know what I mean?
Hmm.
So as this stuff is moving around, it could be getting denser in some areas.
Oh.
Right? It's not water
Yeah.
that you can't compress. This is more like air, right?
Hmm.
It could be like in the bottom left corner over here, it could be getting pretty dense there. Right? You guys kind of see that?
Yeah.
So think about this as in terms of airflow more than water flow, because water flow will screw with your mind because it's what's called a divergence-free vector field. Flows of water tend to be divergence-free because they can't be compressed.
So in this case, the negative, what if we did, for some reason, get a negative, would that?
That would mean that
More is coming in, basically.
yeah, that more stuff tends to be inside the sphere than outside, or inside the cube rather, and that would be that air thing, right? Like it's possible that more stuff is getting packed into this cube. You guys see that? In this case, that would mean that the kind of the density is going up in there. Keep in mind again that these things are sort of allowed to create matter, right?
Yeah.
So again, isn't quite right with.
Like I said.
Your intuition is just a little bit broken here.
Yeah.
So like I said, air is spontaneously appearing in the center of the cube and going outward.
Yeah, that could totally be the case. Right, like air could be created inside this cube and then it could be flowing out through it, right? So it might not be like this outward flux, right? Might not be saying that there's any less density in there. It could just be that it's being created inside. To say that there was a lower density might be a reasonable interpretation given a physical problem, right? But just given a mathematical model, who knows?